Hello, and how you doing? This is the third installment for Unit 9. I think I've been calling it Unit 10, but Unit 9 earthquakes. Remember, the tectonic activity is actually caused by plate tectonics, and whether we have it spreading apart, divergent, or tension, whether we have it coming together, convergent, or compression, or whether we have it moving along the transform fault or the shearing forces. Anytime this rock builds up enough stress, the rock breaks, and when it breaks, it sends out seismic waves in all directions. It's that buildup of stress and finally the release of that kinetic energy, and then it travels out in all directions, some of them going through the earth, body waves, and some of them actually going across the surface, which we call surface waves. Seismic waves, they're going to cause deformation. Remember, we talked about elastic deformation, put the stress onto it, release the stress, and the rock bounds back. Plastic, where you put the stress in, release the stress, and the rock changes shape and stays that way. And then the rupture, where it actually bounces back to the original size and shape, except that it's now broken. Seismic deformation can be found in two ways. It's called static and dynamic deformation. Static deformation is actually the permanent displacement of ground due to the event. So if you actually see roads fall, if you see cracks open, if you see California slide down into the ocean, which will never happen, or slide up towards Alaska, which a lot of it is headed, that's the static deformation. After the earthquake, the formerly straight line that is distorted is actually going to change back to be a straight line, except it'll be offset. So imagine a road and break the road, and part of the road moves to the left, part of the road moves to the right, part of the road moves up, the other part moves down. Whatever case you get, you're going to get that elastic rebound. The stress is released, but the straight lines have been distorted. Second type is called dynamic deformation. This is very much like sound waves, and they radiate out in all directions. They allow you to hear the earthquake, see the earthquake if the seismic waves are enough, and you definitely can feel the earthquake. Most plate tectonic energy from that rupture is actually going to be the static formation, changing the shape of the rock, but up to 10% of it can actually be this dynamic. And what happens is it radiates out in all directions, and we call these waves that radiate out. Only 10% of the information, or 10% of the space, is actually going to be seismic waves. There are two different types of seismic waves, body waves and surface waves. The first one we're going to talk about is body waves, because these are the ones we're going to use to actually determine the location of earthquakes, the magnitude of earthquakes, and how much damage it's going to be. And there are two types of body waves. We have primary waves, which are called P waves. They're called primary because they're the first ones to arrive at a location after an earthquake, and that's because they are the fastest waves, and these are traveling at about 6 kilometers per second. We also have S waves, secondary waves. These are more complicated waves, and I'll show you what they look like next, but these come in second. They only travel at 4 kilometers per second. Still a pretty good clip, but they don't travel as quick as the primaries. These are primary waves, and if you take a look, they're basically shape changers. They arrive first. They're called pressure waves. They're analogous to sound waves. They travel out in all directions. They go up and down. If the earthquake is strong enough, you can hear the earthquake. You definitely can hear it if it starts rumbling and cracking and knocking things off walls or knocking walls down. Particle motion's along the same direction as the wave. So what happens is the motion is going this direction. It's analogous to a person running with their arms to their sides, basically throwing their arms forward and back, the quickest way to run. This actually shows it going in a straight line. That's not what happens. It really happens like this one over here with a point source, but it's going out in all directions. And basically what it's doing is it's changing the volume of the things. It's changing the size of the things. And because it's a size changer, it actually goes through different types of materials, and I'll talk about that next. P motion, P wave motion, if you talk about a slinky, you can see the motion goes in the same direction as the slinky. You can actually watch these things, and they move back and forth, but the energy actually moves through it. So the particle moves back and forth, but the actual energy in the wave, the compression and expansion, actually happens in the same direction as the wave is traveling. S waves a little bit more complicated because the motion is actually perpendicular to the wave, and it spends some time going up and down, and this is analogous to a person running with their arms going sort of side to side, where you're actually turning your body clockwise and counterclockwise, which takes up some of your forward motion. And this is the reason these waves don't travel as quickly. S waves, as you can see, they're actually more like a shape changer. S waves are sideways movement. Rock is moved from side to side as the wave passes. It's like water waves. Rocks are more resistant to sideways motion, so the S wave travels a little more slower. And you actually take a look at that and you can see that the wave travels through and it's actually bending the shape of the things, and you can see they're doing this way, and they're not rotated. They're actually, because they're moving out and sort of sideways, and you can see it on the next one, they're moving out, but they're also bending the things sort of in a circular motion. They don't travel as quickly, and these are shape changers. Seismic waves, we can look at, let me go back because that's not a shock wave that I could attach. We'll go here and we're going to say OK. Internet Explorer does not like to open up shock waves. Okay, so we're going to look at surface waves, vertical motion. And you can see it's caused a lot of rocking and socking. That actually is the S wave. We look at the surface waves horizontal. These are traveling more zigzaggy. And then we watch P waves. P waves compressing and extracting. S waves moving up and down as well as going forward. Surface waves, these are actually called love waves, and I'll show you those. They're actually going sort of up and down and side to side, and these are called, I forgot the name of these, but I'll show those to you later on. These are the two that actually cause a lot of the damage, along with the S waves. The P waves don't seem to cause much damage, so I'm going to minimize that. Go ahead and minimize that. Go over here. Surface waves, they come in two different types as well. They're a lot slower because their motions are very complicated. We have what are called love waves. Love waves move on an X and a Y as well as a Z. So you see them kind of going this direction. They're also sliding side to side motion. I'll show you an animation. And the other one are called Rayleigh waves. Don't know why I can't remember that one, huh, Rayleigh? Okay, they also have an X and a Y, direction of propagation, the direction the wave goes, but because they actually have a little simpler motion, they don't travel. They are slower than P and S waves, but they're actually not as slow as the love waves. So L waves are long, they're up and down, they're side to side. These are the slowest because of their progression, although they're still moving kind of fast. These are like 2 kilometers a second. That works out to about 1.5 miles every second. It's pretty darn quick. The other one, Rayleigh waves, they're a little bit more like water waves. They're a little faster than L waves, but they're still not as quickly, and they move a little different. And this is the actual propagation of them. And if you take a look, the love waves or the L waves don't get to this side as quickly as the Rayleigh waves do. So that's basically the section I want to talk about today: seismic waves and propagation of the body, and surface waves, and then talk about how the motion of each of those works. Next thing we're going to do is talk about epicenter location, magnitude of an earthquake, whether we're talking Richter or Mercalli system, and then we'll actually talk about epicenter location, and we'll do a lab on that. Thank you much for stopping by. Appreciate it.